The final talk in this session will be given by Professor Eric Cornell. Professor Eric Cornell is an adjunct professor of the University of Colorado and the JILA NIST. He shared the 2001 Nobel Prize in Physics with Carl Wieman and Wolfgang Kittler for the achievement of Bose-Einstein condensation. So today, his topics will be rather different. The title is The Three-Legged Stool. Please join me to welcome Eric. So once again, you are able to type your questions in, even I'm unable to see. And please also type your name in and then your institution there as well. Okay, Eric, please.
Okay, I'm going to try to share my screen. Is that working? Can you see my slides?
Yes.
Okay, so I'm an atomic physicist, but I'm talking at a particle physics and cosmology conference. And so to establish my credentials, I'm going to quickly review for us particle physics and cosmology. Particle physics is based on atoms. Inside the atoms are nuclei, inside those are protons, inside those are quarks, and then there's other things we don't know about. So that's particle physics, as far as I know. Cosmology, I know a little bit more about. My understanding is that the sun is at the center of our solar system, and gravity drives the planets, and that the stars we see out there are just more suns. And moreover, galaxies, those fuzzy things we see out there, are just collections of stars. And then more recently, I've learned, for instance, this morning, that we live in an expanding universe. There's dark matter, dark energy, inflation. At one time, there was a Big Bang. Okay, so just to show that I know what I'm talking about, that's what I know about high energy physics and about cosmology. I know that particle physics and cosmology have unanswered questions. Among them are, what is the dark matter? There exists dark matter. What is it? There's a matter, antimatter asymmetry. Particle physics has sort of inconsistencies in its theory at high energies, and how could we learn more is the question I want to ask. How do we learn more? Maybe if I ask that question coming to this conference as an atomic physicist, the question, there's going to be some pushback, and the question would be, what business is it of yours, Mr. Badinsky, atomic physics physicist? Why do you think this is even in your purview? And so my answer is based on the metaphor of this little baby here. This is the time the picture was taken, it was quite a young baby, but you can see somehow from the format of this picture that it was a young baby a long time ago. Atomic physics is very old. I don't know if it really, if you want to say it starts with the periodic table, but certainly somewhere around there is where I would sort of think of the beginning of atomic physics. And for some 6 decades, talking about the middle of the 19th century and on, atomic physics was the physics of the smallest known particles. Smallest things we knew about was atoms, and AMO physics, not that we called it back then, was that physics. When J.J. Thomson used his cathode ray tube to look at electrons and so on, you know, we think of that, the atomic physicists would like to lay credit to that. So we think of the E in the cathode rays are the E in Deep Daymop, which just celebrated its 50th anniversary. When we look at that object up there, when we look at that tube, I'm wondering if I can see my mouse. Can you see my mouse or my cursor here? To me, that looks very much like an atomic physics experiment, a modern day atomic physics experiment, but it also looks a little bit like a particle physics experiment, doesn't it? It's got a beamline and so on. The periodic table, even these measurements of charge to mass ratios of electrons, these were not compelling arguments for the quantized nature of matter. But Brownian motion and Millikan's oil drop experiments are. And so that sort of takes us from ratios to reality. This is a picture of Millikan's oil drop experiment. And I look at this and I can, as an atomic physicist, I recognize something that looks a whole lot like a modern day atomic physics experiment, just kind of nascent, if you want to say. And similarly, these beamlines, this of J.J. Thomson looks like a lot like an atomic physics experiment. But I imagine that both of these look look essentially quite familiar to a high energy physicist as well. The apparatuses don't actually look that very different. We've got vacuum chambers, we've got electronic leads leading in, we've got various detectors, fluorescence screens, or microscopes to detect. These look a lot, these could be either a very early AMO physics experiment or a very early particle physics experiment. And we'll call it a baby, but as AMO physics was 6 decades older, we're going to say that this baby is our baby. The particle physics baby is the baby of atomic physics. And our baby has grown up to be big and strong, and we atomic physicists are very proud of it. There's a big, strong, grown-up particle physics these days. But these days, we sense that our baby needs us again. And when your baby needs you, who can say no? I mean, who can say no to this baby? How do we learn more about the stuff that makes up the macro and micro universe we live in? But my next metaphor is out of the 3-legged stool. One leg of the stool is telescopes and telescope-like things. This obviously is a conception, I guess, of a very large new telescope. I include LIGO in the world of telescopes, and neutrino detectors in the world of telescopes, and the satellite, this I guess is Kobe. This is sort of, I think of all these things as variants of Newton's or Galileo's telescope, if you like. This is one way, and a very, very productive way, as we've learned from 2 earlier talks this session, of learning about our universe, learning about cosmology. Another leg of the stool is accelerators. This is the LHC, and a very successful, and I think maybe the largest scientific instrument ever built, is my understanding. But to take the sort of next step forward in the direction of particle physics will require a more powerful accelerator. And that may require in excess of 20 years and quite likely well in excess of $20 billion. So if we look at these 2 legs of the stool, we might have to wait a long time before we reach higher energies using accelerators. And this is a somewhat more subtle comment, but the thing about the universe is that it happened only one time. By its very nature, you can't do experiments on the early universe. It's already happened and it won't ever happen again. You can derive statistics from looking at different places in the universe. But as an experimental physicist, we sort of have this idea that part of what we do is we manipulate and then we see what happens as a way of more rigorously establishing causality. So I think there's room for a 3rd leg, which I'm going to call precision measurement. Here we're using a caliper to measure a very old fossil. And of course, the old thing that we really want to measure is the very beginning of the universe. So by making precision measurements, we can understand old things, whether they're fossils, in the case of this metaphor here, or the early universe. These are what I think of as the 3 legs of a stool that we can use to understand the early universe and new particle physics. Okay, we're going to have a metaphor shift coming up. Don't throw out the baby with the Batman. Here is the Batman overlooking Gotham City. The bat signal has gone up. We think that particle physics needs us, and we're answering the call. This is a long-standing tradition of precision measurement of contributing to particle physics. I think maybe the most famous example is the electron's magnetic moment. The electron's magnetic moment is some numerical factor times some combination of fundamental constants. And the first observation, and this was in its day a precision spectroscopy result based on fine structure in atomic spectra, is that this constant is not 1, which would sort of be the default idea, but 2. And this was the early triumph of the Dirac equation, which was the first attempt to reconcile relativity and quantum mechanics. Beyond that, there was quantum field theory, and one of the 2 first tests of one-loop quantum electrodynamics was the fact that this constant was not 2, but something slightly different than 2. In its day, this was an extremely precise measurement to measure the difference between of the G factor. It's not exactly 2, it's about 1% different or so. This was a precision measurement, and it was the first test of this sort of one of the great triumphs of early particle physics, quantum electrodynamics. These days, still measuring the G factor still more precisely they've been able to compare experiment and theory out to, I think, at least 4 loops or something like this. And this is by far the best test of many loop perturbation theory. So this is, again, precision measurement contributing to the world of particle physics. Another early triumph of sort of precision measurement and particle physics was the Lamb shift, which was sort of the second half of the test of electrodynamics, the fact that the hydrogen atom has a fine structure, basically. So we've got these various different things. Molecular spectroscopy, again, in its day, looking at the vibrational and the rotational constants inside molecule spectroscopy was actually the thing that drove the development of angular momentum algebra, which is one of the sort of underlying theories of quantum mechanics, one of the underlying principles of quantum mechanics. Since then, and everything I've talked about so far has been sort of 1940s era stuff. There have been fabulous increases in the possible in precision. For instance, in measuring time, has our ability to measure time accurately has gotten 9 orders of magnitude better since the 1940s, it's comparable to the idea of accelerator energy getting 5 orders of magnitude better in a similar amount of time. So there are possibilities, we think, of contributing again, and because of sort of advances in technology, analogous to the advances in technology in accelerators. Beyond measuring frequency, AMO physics and precision measurement has tricks such as atom interferometry, using ultra-cold atoms as force centers, using more sophisticated quantum mechanics to enable sensitive measurements beyond the shot noise limit, and so on. I'll just show a few examples of that. This is a atomic interferometer, analogous to interfering through laser beams, but you interfere 2 beams of atoms, and very sensitive to all sorts of inertial and other perturbative forces. This is from Mark Kasovich's group. This is a 10-meter tall tower, which he separates 2 wave packets of atoms, brings them back together again. Measurements like this can be used to make extremely sensitive measurements of the fine structure constant, probe fundamental sources of quantum decoherence, look for fifth forces, things like this. This is my foray into particle physics theory, so I ask your indulgence. My understanding of why force laws so often decay as 1 over r squared is due to the fact that we live in 3 dimensions. We live in 3 dimensions, and you just sort of invoke the idea that flux is conserved, and the area of the sphere is increasing as r squared, and so the field amplitude must be decaying as 1 over r squared. If instead you lived in 2 dimensions, the field amplitude would decay as only 1 over r, and you'd see a very different force law. If you happened, just hypothetically, to live in a world where you have you live in a 2-dimensional world, but you have one of those, you live in a 3-dimensional world, but one of those dimensions is all curled up. So you live in a 2-dimensional world except at very short range where you have a curled up dimension. You would observe a crossover. The force law would go sort of as 1 over r squared at short distances and 1 over r at longer distances. Okay, so now if you live in a, what the heck is it, 22-dimensional world, I'm not sure, then you might expect also to see crossovers in the force laws as you go away from the distances at which these extra dimensions are curled up. So if you study precision measurements of the 1 over r squared force laws and see deviations, you see evidence for possible curled up dimensions. And this is just an exclusion plot of people trying to do exactly that, basically measuring the force of gravity at distances down to microns. And so far, I must say that they've not seen any evidence, but that's okay. These experiments are ongoing. Further ideas of precision measurement connecting to particle physics. We revisit the Lamb shift. Again, this is supposed to be, I didn't really explain this before, this is the ground state of the hydrogen atom. This is the first radially excited state, and if you measure this fine structure very precisely and compare it to theory, you can see quantum electrodynamics, yes, but you can also measure, in essence, the size of the baryonic core of the hydrogen atom, of the proton at the center of the hydrogen atom. And you can do this with two different kinds of hydrogen atoms, one in which you use electrons and one in which you use muons as the negative charged particle orbiting the proton. And there has been a conflict. It measures, these two experiments measure, you can use these to infer the size of the proton, and you get a different result for the charge radius of the proton. So these are discrepancies that can be tracked down. We think that electrons and muons should be really, really, really similar, but maybe not. So these things are, by making these precision measurements, we can look for discrepancies and anomalies that might point the way to new physics. Very popular in the world of precision metrology are searches for new sources of CP violation, of T violating physics of one kind or other. And this is an extremely well-motivated experiment, and they're motivated by, it's basically the astrophysicists have put together evidence from Kepler, from Chandra, from Kobe, from LIGO, plus theory input from René Descartes to determine that the universe in fact exists. What I'm talking about, of course, is that there's very strong evidence that at the very early time of the universe, the antimatter was all used up before the matter was, when these things were recombining. There's baryon, anti-baryon asymmetry. That's why the universe exists. And that's evidence for CP violation beyond what we see in particle physics today. So atomic physicists are looking for other sources of that. I'm looking for that. My group in JILA is looking for that. We're looking for the electron's electric dipole moment. And we do that using molecular ions. This is an experiment ongoing now for 10 or actually going on 15 years at JILA at the University of Colorado and NIST in Boulder. The experiment is done for all these, for many, many years now in collaboration with Jun Yi, my colleague in this business. He's an amazingly accomplished laser spectroscopist, maybe the world's greatest laser spectroscopist, in my personal opinion. And I've been working with him now for going on 20 years. And we've had a group of talented graduate students and postdocs. There are many theory collaborations, and we've been generously funded by our beloved National Science Foundation, National Institute of Standards and Technology, and various private foundations. Thank you to them as well. Here's a recent picture of the group, and recent members of the group who've gone off to get faculty jobs are shown in the upper corners there. How do you measure the electric dipole moment? Conceptually, it's very simple. You've got a magnetic field, you've got an electron, which could be spin up or spin down. If in addition to the magnetic field, you also have an electric field, then the resonance experiment, where you flip the electron spin over, that the energy to flip the electron spin over is proportional to the magnetic field, but there's also a slight splitting of those resonance curves, which has to do with whether the extra electric field is parallel to or anti-parallel to the magnetic field. The electric field would dot into any electric dipole moment that an electron might have. So you're trying to measure, to resolve two resonance lines. Basically, these are electron spin resonance lines. The resonance frequency of the RF, the radio frequency, you would need to shine at this electron and cause it to flip over. To do a very good electric dipole moment experiment, you need to apply a really large electric field. You'd like to have really long coherence times to make these resonances narrower and easy to distinguish. And then you'd like to have good counting statistics so you can find the center of these two lines and distinguish them with more precision. Of course, that's hard to do because a large electric field causes an electron to go flying away. So we get a large electric field and keep our electron from flying away by embedding our electron into a molecule. If you have a polar molecule, this is supposed to be the positive atom and the negative atom. You can get a very large internal electric field, a much larger field inside a molecule than you can conveniently apply in a lab. In our experiment, we apply a field in our lab of only a few tens of volts per centimeter, but we get 9 orders of magnitude larger electric field effectively applied to the electron spin. So we do the experiment not on the electron spin, but on the molecular spin, which has inherited the electric dipole moment effects of the electron inside it. To get a long coherence time, our molecules are trapped. It doesn't particularly look like this, but we have long electrodes which are charged and confine our charged molecule. we can keep them in there for many seconds and see extremely narrow resonance lines on the order of a few hundred millihertz. I'm not going to walk through the experimental procedure, which is extremely complicated. Involves a great deal of lasers, very large number of lasers. We use the lasers to initially prepare the molecule in a particular quantum state, and additional lasers to read out the final quantum state of the molecule. The molecule itself is made, our favorite molecule, which has all the right symmetries and sensitivities to give us a good signal to noise. Our favorite molecule is hafnium fluoride plus, and we actually make that using in situ. Basically, we do the chemistry in the middle of the vacuum chamber, create the molecule, ionize it, prepare its quantum state, and then over the course of about a second, give or take, maybe some 700 milliseconds, we allow its internal quantum phase to evolve. We read it out using various atomic molecular tricks. And we see essentially the precession of the electron spin inside the molecule. And in this particular case, it's evolving very slowly. You can see over the course of about 1 second, it's oscillated about 20 times. The bias magnetic field is extremely small, so this is a very low, you could call it a radio frequency signal if you want to, but it's a pretty low radio frequency station. And we measure these electron frequency, this frequency of the electron wobbling, the electron spin resonance frequency, in the presence of the molecule electric field pointing one way or pointing the other way, and we fit these things and extract very precise frequencies from them, and we look for small changes in these frequencies as we change the direction of the electric field, which we do simply by changing whether we have the positive atom on top or the negative atom on top. We can flip the direction of the electric field by flipping the alignment of the molecule. So this is a differential measurement we can use to very sensitively detect electron dipole moments. We do these experiments on atoms in a trap. We would like to have extremely uniform fields in our trap as a way of characterizing that, and this is sort of as a proxy for looking for many different sources of systematic errors. We put the electrons in the middle of the trap. We apply various electric fields the electrons, the molecules, the molecular ions we put in the middle of the trap. We can apply supplementary electric fields which move the molecules around so its equilibrium position is at various different places in the trap. And as we do, we see the various resonant frequencies shift. So this is as we move the molecules a few millimeters to one side or the other in the middle of this trapping volume, which is many centimeters across. We can see that the frequencies are shifting. The colors here refer to also moving the molecule up and down in the z direction. You would anticipate, you would like to see all these different points all collapsing onto the same frequency. They don't, and we know exactly why. By measuring how the spatial dependencies of these different frequencies, we can characterize all sorts of field inhomogeneities in our experimental apparatus. We can model them. We know the source of this curvature. We know the source of this residual slope. We know why these three lines aren't asymptotically kissing each other right here. These are all different imperfections in the trap. We can characterize them, we can correct them, or at least correct for them. And in this way, convince ourselves that we've made an extremely precise measurement. A key aspect of making a precise measurement, especially when you're making a measurement where you really have a preference. As experimenters, we would love to determine the electric dipole, measure a non-zero electric dipole moment. So when you want to measure something very badly, you should try and do something to keep yourself from seeing what you want to see. So we take all of our data blind. We collect the data, the computer lies to us basically, adds a little offset to all the data we collect, and we use other characteristics of our data, the scatter of the data, its systematic dependencies on various perturbations, to convince ourselves that we have an accurate number. And then, only then, do we tell the computer to stop lying to us, to unblind the data and tell us what we got. The unblinding moment for our most recent precision run, which we unblinded in 2017, was one of the more intense moments in my scientific career. We basically got everyone in the collaboration in the room, and we projected the answer on the wall and told the computer to unblind. And In fact, the number we got was consistent with consistent with 0, but with a very high precision. Here's sort of a historical plot showing how the precision of the limit, all these measurements of the electron's electric dipole moment have been consistent with 0, but the error bars have been getting smaller and smaller versus time. These are various atomic measurements. Starting in red here are this new generation of molecular measurements. The ACME group, the Harvard-Yale collaboration, had a very impressive result in 2014. JILA came along and had a very similar result a year or two later. These two measurements, the fact that these measurements were consistent with 0 was very inconvenient for the sort of minimal supersymmetric model. But of course, in those days, right around that time, around 2015, the minimal supersymmetry was encountering a lot of inconveniences, also from the Large Hadron Collider. So rather than disproving or disfavoring supersymmetry, I would say these results really more corresponded to kicking supersymmetry when it was down. Shortly after we made this measurement, Harvard and Yale, the ACME group, made yet another measurement of another degree higher in precision, which seems sort of gratuitous. As one of my favorite television shows, Cornell, says, that's just rude to do that. That was, really a little bit too much. We anticipate shortly having a measurement, probably within a year or so, of similar accuracy. And we have a third generation project coming up, which will do about another factor of 10 beyond that. We're no longer really motivated by making fun of supersymmetry, because that would be kicking supersymmetry when it's down. We're really motivated by the fact that CP violation exists. The astrophysicists tell us that the universe exists, and that tells us that CP violation exists. This is as these various sort of null experiments go, this is a particularly well motivated one. It really seems that somewhere around here we should be seeing something. We'll see. We don't actually measure just the electric dipole moment. We measure a linear combination of the electric dipole moment and this other parameter in a particle physics Lagrangian called CS. And our experiments put together, basically, you might ask, why do two measurements of similar precision? And it's because our two different experiments, our experiment and the ACME experiment, have different sensitivities to the electric dipole moment and to this other parameter. And by putting them together, by putting the ACME experiment together with the hafnium fluoride experiment, we can put tighter and tighter limits on both of them. In this case, this is the only allowed space left over. What is this term CS? The electric dipole moment of the electron, that's relatively easy to understand. The way I understand this term CS is this is near the hafnium, the core of the hafnium atom. I've got the nuclear density of the hafnium atom. I've got the electron density. If I apply a nearby, I put the fluorine atom. I basically have a negative atom nearby. I distort the electron density. And then the electron density has, of course, is polarized, so there's a spin density. And basically, there's a term which is the gradient in this nuclear density times the spin, and basically the density of the spin times this parameter. That should give us a term, an energy term, basically. And it manifestly violates CP. So that's sort of a motivation for why this term also is interesting. I'm going to take a quick turn to talk about dark matter, which we've heard so much about. This is not my slide. This is certainly not my experiments, my data, or my images. I borrowed this slide from Mariana Safronova, former chair of DEMOP. She in turn assembled these from many different groups. I think this is obviously a gross oversimplification after hearing some previous talks, but say galaxies are rotating too fast. There's a lot of mass out there we can't see. Its density in galaxies is about 1/3 of a proton per cubic centimeter. What is it? Most likely it's particles and not tiny black holes or little Jupiters floating around. We know that they must be going about 300 kilometers per second, because that's in our galaxy, because that's from the virial theorem. we can ask, what is the mass of the dark matter particle? And the mass of the dark matter particles are very well established. They must be somewhere between 10 to the minus 22 and 10 to the 27 eV. The high end here, this is just the Planck energy, and it doesn't necessarily have to be less than the Planck energy, but it would be complicated if it were a single particle any more massive than that. And down here, the particles can't be any less massive than this, or they won't, their wavelength in essence, basically they won't be gravitationally bound to galaxies. So if we know the local density and we know the local velocity and we have a particular mass, we don't know what the mass is, but if we pick a particular mass, we can calculate the coordinate space density, the momentum space density, and the phase space density. And what we find is that if the mass of the axion is less than about 10, if the mass of the particles that are making, which I'm jumping ahead of myself, if the mass of the particles which are making up the dark matter is less than about 10 eV, then the phase space density of these particles is greater than 1. So what is the spin of these dark matter particles? Well, here are three likely possibilities, 0, half, or 1. And we know then that if we're to this side of, this is the 10 eV mark, if we're to this side of 10 eV, then we know that the particles are degenerate. And therefore we know that it can't, this region is forbidden. They can't be fermions, they can't be spin 1/2 particles with this kind of density, this kind of mass, because basically the Fermi energy would be so high that they would not be bound to do small galaxies, not be bound to galaxies. Whereas if they're in this region, they must be, I'm calling them Bose-Einstein condensates, basically degenerate Bose clouds of molecules. This little picture is getting in my way. Maybe I'll move it out of the way. So we've really boxed in the dark matter particles here. What are the odds? What are the odds that there exist in the universe, in the galaxy, this degenerate Bose gas of dark matter particles with spin 0 or spin 1? Well, I think we can say what the odds are quite precisely. First of all, we have to have some notion of what are the probability of the axion's masses being distributed between 10 to the minus 22 and 10 to the minus 27. And I'd like to assert that it can't possibly be linear in that sort of linearly distributed along here, because if it were, all but 90% of the probability would be at this upper little square here. So I think pretty general principles, I'll say the probability of the dark matter particle is uniformly distributed, logarithmically uniform distributed across this possible regime. This is about halfway through, so we can see there's 1, 2, 3, 4, 5, 6 possible regions, and 2 of those 6 possible regions, actually one of them is forbidden, so there's 5 possible regions, 2 of them are condensate regions. So with quite a deal of precision, I can say that there's a 40% chance that there is going to be a condensate. Professor Peebles, do you buy into this? I'm saying there's a 40% chance of I can see him shaking his head. I think this is pretty rigorous. All right, it's supposed to be a little bit of a joke, but in fact, it's also sort of suggested it doesn't, in the world of parameter space, this is not such a crazy space to be. What would be, if this were some sort of quantum thing, some quantum gas, it would have a quantum phase frequency, which would be proportional to its relativistic mass, its relativistic energy based on its rest mass and any galactic velocity it has. And this is relatively small, so given that the variable velocity is small compared to the speed of light, so this oscillation frequency is relatively unsmeared out by the Doppler shift, and it's a narrow resonance of about a part in a million. Given our 5 minutes, okay. Yep. So is that 5 minutes? Okay. So given that we have some estimate for the range of the axion, this works out, the period of these oscillations works out, the frequency of these oscillations works out to somewhere between 1 over a year and 1 over 10 to the 14 hertz. And this is very convenient for tabletop experiments, because a 1-year experiment is a reasonable length experiment to run on the one hand, and on the low end, this period is not an inconvenient, is a convenient period for experiments. And on the high end, this frequency is fine for lasers and what have you. So all in all, AMO physics is well suited to look for frequencies in this region. Is a dark matter bosonic field really a Bose condensate? My understanding is, and here I am getting over my head, is there is a model that suggests that you could come up with a model that suggests it's a spin zero particle, and it started off as basically as a condensate, but then it collapsed gravitationally into galaxies, picking up a lot of random thermal velocity. But there's evidence that the dark matter is not thermalized, and therefore we would imagine that it's still basically sort of a thermally fluctuating bosonic field, macroscopically occupied, but thermally fluctuating field. If you wait, you don't know exactly what this frequency is because you don't know what the mass is, but at sort of 10 to the 6 times that frequency, the phase and density of this gas will be decorrelated. So the question is, would this oscillating phase give rise to an oscillation in various physical parameters? For instance, the electron EDM. If we measure electron EDM, what might we expect it to oscillate because of this presence of this field? Our colleague Victor Fenblom says that the connection of this field to the electron would be very, very small, probably not visible. But the connection not of the axion field or the axion-like field, not to the electric dipole moment, but to this CS term, that is should be non-negligible or could be non-negligible based on other possible astrophysical limits. So basically, imagine an axion is sort of coming in and getting absorbed in essence by a gluon, and giving rise to a time oscillating field because this process would be sensitive to the phase of this field, a time oscillating CS term, possibly. So there's a reason. So we went to look for that. And basically the way we looked for that is we had made many measurements in our existing measurement of the electric dipole moment. We made many measurements, took the average. We could instead sort of see whether these measurements as a function of time. We could see whether we could account for some of this by fitting it to sinusoids. You could see this particular sinusoidal frequency is not a good fit to the data. And in so doing, we're sort of sensitive to this portion indicated by this arrow of these regions of possible bosonic fields. Here's our best fit to any oscillating frequency of the electric dipole moment. We have in the world of particle physics, we say we have a huge look elsewhere effect because basically these are many different frequencies ranging from almost 10 to the minus down around 10 to the minus 8 hertz up to almost 1 hertz, and we have, when in essence we are testing 10 to the 7 linearly independent hypotheses, and any one of them could have a quantum fluctuation up. So we had to spend a lot of time thinking about the statistics of that. We were helped a lot by Ben Pelkin and Ben Brubaker, who are veterans of the axion search, in their case, usually using superconducting cavities. And moreover, they're apostles of St. Bayes. These are we use a sort of a Bayesian approach to these things. I'm basically out of time, and I'll just give you the bottom line, which is no, we don't see any time varying thing, any significant time varying effect. This is the curve, the testing to that. And we can put our exclusion on top of other possible exclusions for the same term in the Lagrangian. And we're not, this is the part that we've excluded, we're not completely competitive with the neutron measurement or with various indirect cosmological arguments. But the experiment came basically for free. We didn't design an experiment to try and test these things. Had we designed an experiment, we would have built an experiment which was sensitive to basically nuclear effects and not electron effects. Our electron measurements are so sensitive that it has some sensitivity to these couplings between axions and gluons. Okay. Wrapping kind of up here, there are many other possible time dependencies you could look at now that we have these wonderful clocks. The universe gets older and bigger every year. Every year, the universe gets older and bigger by about a part in 10 to the 10. Which is actually not such a small number compared to the accuracy of clocks, which is 8 orders of magnitude more stable. So one can build various clocks, compare them to each other, and look for time varying changes in the constants, which might somehow be coupled to any sort of field which is getting diluted as the universe expands. not going to talk any more about that. Looking over the next 20 years, I think there's going to be many new precision measurements, precision measurement particle physics results. Probably a lot more precision measurement particle physics results than accelerator results. This is, I'm not saying they're better results, it's just that these experiments can start now, whereas the next generation of accelerator experiments might not start for 20 years. They might not be very interesting results, they might be largely non-results. And we are looking for help to make these results better. We have a wish list for theorists who are interested in new particle physics. Is it possible that we can parameterize theory suggestions in such a way that we can compare experimental ideas one against the other in sort of an agnostic general framework? Saying is, we could measure a lot of different things very, very precisely. Which of these measurements would be most interesting? I'm not sure that's possible, but certainly there are, theory can provide sort of more specific pointers. For instance, there are very general ideas that let one compare the discovery potential of a G-2 measurement of the magnetic moment of the electron or the magnetic moment of a muon if you are trying to look for evidence of particles much heavier than either. That's not such a complicated thing to do. I would love it to sort of see various sort of effective field theory ideas that we could use without doing elaborate calculations, used to sort of compare one against the other and try to understand which sort of experiments might lead to the most interesting results. Given that there are, with the advent of all these new precision measurement techniques, there are a lot of different things we can look for. I see this as a third leg of a stool, of the three-legged stool, the stool that we use to look for new particle physics and new cosmology, or better cosmology, better particle physics, new particle physics. And I'll go back to our previous metaphor, which is that Batman needs to take care of the little baby. All right, thank you for your attention. That's all I have to say.
Thank you very much, Eric. All right, we have a few minutes for some questions. I see many questions here. We will have to be selective, and my apologies. So let me see. The first question I'm going to ask you is from Bill Phillips, JQI. We have a CPU violation in the standard model, but too small for matter asymmetry. How big does the EDM need to be, and can we see that minimum?
Yeah, unfortunately, that it's not so easy to go from large enough CP to create baryon antimatter, matter antimatter asymmetry, to size, required size of the electron electric dipole moment or anything else. These things are very model dependent. It was one of the great things about the supersymmetry, is it was kind of a framework. There were a lot of adjustable parameters in minimally coupled supersymmetry, but at least it gave a order of magnitude estimate, which was something like 10 to the minus 27, 10 to the minus 26 e centimeters, with the electron dipole moment limit now 1,000 times better than that, smaller than that. It tells us that either supersymmetry is wrong, or else the various parameters are fine-tuned to give us a small electric dipole moment. But once we move away from that framework to whatever else anyone else's favorite framework is, it's really difficult to say what would be the number that would be you really ought to see. It's really not possible to say. It's sort of the point of my last slide that I showed. Yeah, you could use more sort of general principles guidance, as we used to have from supersymmetry.
Okay, thank you, Eric. So the second question is from Marcel Delmator. Can you hear me?
Yes.
Can you hear me, Eric?
Yes, I can hear you.
The second question is, what role do you see atomic clocks could play in shedding light on some of the fundamental questions?
Well, for me, atomic clocks are more or less just a proxy for precision measurement. you know, if you want to measure anything precisely, if you see an experimental quantity which has more than 5 digits of precision in it, almost surely that quantity was measured by converting it into a frequency and then measuring the frequency. So that's where the clock comes in. Basically, the job of the precision metrologist is to try to figure out how to take the interesting piece of physics that he or she wants to probe and convert that piece of physics into a shift in a frequency or shift in a time and compare that against an atomic clock. So atomic clocks writ large, I mean, in general, there's a specific sort of atomic clock where you're trying to redefine the second or something like that, the duration of a second. But more generally, atomic clock really just means a really, really good oscillator based on some physical principle. And what you want to do is compare that physical principle to some other physical principle. At the end of the day, and I blush to say this as an employee of the National Institute of Standards and Technology, seconds are not real. The only thing that's real are dimensionless ratios between various different, very stable measurements.
Okay, thank you, Eric. So the next question is from John Wickerson from University of North Carolina. The question is, it is possible the matter-antimatter asymmetry is from CPU violation in the lepton sector. Are there AMO experiments searching for this there?
Well, you said in the lepton sector, yes?
Yes, that's the
so
question.
That's exactly what the electron EDM is a measurement looking for CP in the lepton sector. And so how did one get from this CP violation in an electron to the proton antiproton asymmetry? I don't really know. But yeah, they're absolutely, the measurement I was talking about today really was a measurement of an electron property. Then someone waves a magic wand having to do with the Sakharov mechanism or what have you, and so this can give rise to effects in the baryons. But
okay,
I'm already, if you could probably guess, I'm already far over my head. At the end, I'm a spectroscopist and not a particle theorist.
Okay, thank you, Eric. Because of the time, I think we may have to stop here. My apologies again to all the other questions that have not been discussed. So please join me to thank all the 3 speakers again, and congratulations to them for their outstanding contribution to physics and also for the Nobel Prize.